First of all, how many of you know how a computer works? Say no. Okay. You don't have to say no. I find most people don't really understand how a computer works. And really, it's so simple it almost hurts. So I'm going to actually take you through a bit of a presentation explaining how a computer works and how they were engineered from the beginning in a very simplistic terminology. And I think if you understand it, then you'll have a good grasp of everything we're going to cover today. So in order to understand how a computer works, you have to understand the principle of a switch. Now, I think most of you will agree that a switch has two positions. What are they? See, it's not that complicated. When I'm talking about a switch, let me explain what I'm talking about. You all know that the computer has a power switch on it. Here it is, on and off. That will turn the computer on. I'm not talking about that switch. I'm talking about little switches inside the computer. There's lots of little switches inside the computer. They're called micro switches. And when we talk about switches, we're talking about the micro switches inside. Now, if I want to give you an analogy, it would be an analogy to your own home. Think of your own home. You have in the basement a power breaker that can turn the power to the house on and off, right? Okay, so if you go to the basement and turn the power breaker off, it means that what happens to the switches inside your house? None of them will work, right? But once you have the power on to your house in the basement, once you have the power on, what does it mean to the switches in your house? They can be on or off. And that's what we're talking about. So the computer, we're assuming that the computer is being turned on now. And inside the computer are a lot of tiny little switches that can be either on or off. Okay, and it's because there's so many different switches in there and so many combinations of how they go on and off. That's why computers can do so many different things. That's really all it amounts to. And generally what we do is if we're drawing a picture of this, we would maybe say on, we draw the arrow up, and off, we draw the arrow that way. The way computer people like to apply mathematical numbers to things. So they've given a mathematical number to these two conditions. Do you want to take a guess? What is a mathematical number to a condition when the switch is on? 1. And what is the mathematical number to the condition when the switch is off? Have you all had this course before? With one switch, there are two possible conditions. And we'll call condition 0 off and condition 1 on. Okay, up to now it's really easy, okay, because it doesn't get any more difficult than this. Okay, that's what makes computers so much fun. It just doesn't get any more difficult than this. We just add more switches. Okay, here's what I'm going to have you do as a little exercise. I'm going to tell you that when the engineers designed the computer, they said, this idea of switches going on and off to process data in the computer is so neat. Why don't we put two switches on each panel? Kind of like the one on the wall there. See that? Two switches together on a panel. And here they are. This is a two-switch panel. And if I was to, I'm going to give you an exercise right now to do it. Just take you a minute or so to figure it out. Take your pencils and tell me how many possible combinations of on and off there are with two switches working. So I'll give you a clue. One combination is both off. I'm going to give you another clue. One other combination is they're both on. Okay, now you got to work at all the rest. So come on, just shout it out when you think you've got how many possible combinations there are. You say 4. 4 is the right answer. With two switches operating, there are 4 possible conditions. We mentioned both off. Or we might, for example, have the right-hand side one on and the left-hand side one off. Or the other way around. We could have this one off and this one on. Or we could have them both on. Okay, everybody see that that is it. There's 4 unique combinations, and that really, beyond that, there are no other combinations. That is it. And we have numerical values that we give these conditions. I just do it by numbering them. This is condition 0, this is condition 1, 2, and 3. I mean, that's how I do it. They're all different conditions, so they all have different numbers, 0, 1, 2, and 3. So that's kind of the technology expanding. You know, by putting two switches on a panel, we have more possible variations of numbers that we can represent in the computer. We can now represent numbers 0 to 3. So if the computer had to store a number 0, it would store it like that. If the computer had to store a number 1, it would store it like that. And if the computer had to store a number 3, it would store it like that. See, computers don't know anything about numbers, letters of the alphabet, or anything like that. All they know is whether a switch is on or off inside. And it's the combinations of ons and offs that dictate what the computer is understanding. And that is it. That's all they understand is that the switches are on or off. What does it mean? What would happen if and this is a little exercise I'll give you to do, I'll give you a couple of minutes to think about it. I'm going to tell you that the engineers thought this was such a great idea, they said, well, let's go and put 3 switches on each panel. 1, 2, 3. We're going to put 3 switches on each switch panel. And now just go ahead and take a moment to think about the number of possible combinations of ons and offs you can have with 3. Now, if you're having trouble visualizing it, say to yourself, pretend you have at home a toaster, a radio, and a light. And you're going to say, okay, the toaster is on, the radio is on, the light is on. The toaster is off, the light is off, the radio is off. The toaster is on, the light is on, but the radio is off. The radio is off and the light is on, but the toaster is off. I mean, and you go through and you work out all the combinations like that, because it's easier to think of things in concrete terms rather than just abstract switches. By the way, some of you may have this in your home. Maybe in the dining room, you may have a panel with 3 switches on it. In fact, I've seen some rumpus rooms where there's 4. But let's say in your house, maybe on the main level next to the dining room, you may find a switch panel in your home where you actually have 3 switches, and you've probably never thought about how many possible combinations of turning them on and off there could be with 3 switches activated. But it's interesting to see how many there are. So take a moment and give me a number when you're ready to shout it out. Just give me a number of combinations that you think are possible with 3 switches on one panel. 8 is the right answer. Okay, well, I'm not going to make you go through the torture of working it all out here, but I will tell you that you can work it out at home, and you'll find out when you work it out, with 3 switches working, there are 8 possible conditions, and here they all are. Of course, we mentioned the obvious one, they could all be off. Or you could have this one on, and the next 2 off. Or you could have this one off and this one on in the middle and this one off on the edge. Or you could have these 2 on and this one off. So we could have this one off and this one off and this one on. Or we could have this one on, this one off, this one on. Or you could have this one off and this one on and this one on. Or they could all be on. And that is it. Those are the unique number of combinations, the only possible unique ways of turning switches on and off that you can come up with. So in total, there are 8 combinations. And watch this. This is called condition 0, condition 1, condition 2, condition 3, condition 4, condition 5, condition 6, condition 7. I just numbered them from 0 all the way on up to 7. So if the computer had to store the number 7, like you type a 7 on the keyboard, to you it's a 7. It looks like a 7 on the keyboard. But the computer doesn't know 7 from heaven. It doesn't know anything. So it just knows that it has to turn 3 switches on. So when 3 switches are on like that, on one panel, that's a 7. You can definitely see that a pattern has developed here. We started off with the idea of one switch working on one switch by itself working. And with one switch all by itself, we said there was 2 possible conditions, and they were on and off, and they were numbered numerically what? 0 and 1. Okay, then we showed you that if we put 2 switches on a panel, we suddenly doubled the number of conditions to 4, and they represented what numbers again? Remind me? 0 to 1 and 2 and 3, right? Then we showed you the next one with 3 switches operating on a panel, and it gave you 8 possible conditions, and they were numbered 0, 1, 2, 3, 4, 5, 6, and 7. Now, having told you that, let's say I was to tell you that the engineers thought this was working so well, they said, hey, let's put 4 switches on a panel. Now, there's a pattern that's showing up here, and you won't have to sit here and do the math on paper or do the permutations and combinations on paper. You'll just be able to do it by probably seeing the pattern. So do you see a pattern? If I was to put 4 over here, you want to guess how many conditions there would be with 4? You're right, 16. There'd be 16 possible conditions, and they go from 0 to what? Absolutely. So if all 4 switches were turned on in the computer on one panel, that would represent the number 15. That's how the computer stores number 15. 4 switches on one panel. That's all it understands is 4 switches on. Doesn't understand 15. It doesn't understand 1, 5. Just understands 4 switches are on. That's 15. Here's the good news. I'm not going to keep you in suspense anymore. I'm going to tell you that the engineers finally decided on a standard of how many switches to put on each panel. And that standard was 8. 8 switches on a panel. So I'm going to put the 8 down here and ask you to tell me how many possible conditions there could be with 8. Now, let's do it sequentially by working up the ladder. If I told you there were 5, what would you guess over here? 32. If I told you there were 6, you would guess, and you're right. And if I told you there were 7, 128. And if I told you there are 8, and there are 8, 256. It's hard to believe there's only 8 switches on a panel that you would go nuts sitting there with a piece of paper for 2 hours and 56 minutes figuring out all the possible combinations of ons and offs. Anyway, the point of the matter is there are a lot of combinations. And you know what? If they're all off, it's called condition 0. And if they're all on, it's called condition what? 255. In fact, it means that the computer can store the number 255 with 8 switches on a panel if all those switches are lit up. That's what the number 255 is to the computer. The panels in your computer consist of 8 switch positions, and this is just one panel. Remember, I told you in a while I'm going to tell you how many panels there are, right? I haven't told you how many panels there are yet, but this is just one panel. It can store any one of 256 possible combinations representing numbers 0 on up to 255. So my question to you is this. What would happen if the computer had to store the number 256? First of all, do you believe that a computer could store the number 256? In other words, have you ever seen anybody type a number as high as 256 into a computer? Yes, okay. So the computer can store 256 somehow. But how is it going to store 256 when we told you that every switch on the panel lit up represents 255? So how is it going to store 256? Go to the next panel. Right, it's going to need a second panel. So you're going to have another panel in the computer with 8 switches on it. And it's going to have this switch turned on. So what's the sum of 255 plus 1? Because with just one switch turned on, this is condition 1 here. And this is condition 255. What's 255 plus 1? 256. Okay, now let me give you a little tougher exercise. What if the computer had to store the number 65,025? 65,025. I will tell you that if you add it 255 plus 255 plus 255 plus 255, 255 times, it would give you the number that we're looking for. It would give you the number 65,025. So would you suspect then that the computer would need 255 panels, each holding the number 255, and add them together, and that would give you 65,025. That's perfectly logical. But then the engineer said, you know what? There's such thing as multiplying. We can multiply numbers. We don't have to add them all the time. So why don't we put 255 on one panel, 255 on the next panel, and multiply the two values together, and that gives you 65,025. So in other words, it only takes 2 panels to store the number 65,025. Here's what it would look like. One panel would look like this, with everything turned on. And the other panel would look like that, with everything turned on. And multiplying 255 by 255 would give you the answer. And that's how the computer would store the number 65,025. But what if you had to store 65,026? What would you do? Well, then you'd need one more panel. Put another panel here, and we'll put it like this. And we'll just turn on the last switch, which gives us a 1. So to get 65,026, we just have to light up one panel, complete, light up the next panel, complete, multiply those 2 panels together, and add the value in the third panel. So it only takes 3 panels to represent the number 65,026. Now let me tell you what these panels are called. Because if you went into the store and you said, you know what, I'm looking for a computer with these switch panels in it, and I'd like to have like a lot of panels. My instructor said, like, we should have the more panels, kind of the better. And they'd look at you and say, well, we don't have computers with panels in them, switch panels, because they don't know that that's what they are. The correct terminology for this, in the wonderful world of computers, every switch panel is referred to as a byte. So we refer to the complete 8 units, the 8 switches on a panel. That is called a byte. And the individual doohickeys, the individual switches on each one are called bits. I have an easy way of remembering this. How many people have heard the expression 2 bits in terms of money? What is 2 bits? A quarter. Well, do you know, it's interesting because 2 bits, if we have a panel like this here, 1, 2, 3, 4, 5, 6, 7, 8, and we take 2 bits, that is a quarter of the number of the switches on that panel. So 2 bits is a quarter the number. Isn't that interesting how that kind of works? Just like money, eh? So if you're having trouble remembering which one's bigger, just think 2 bits. And 2 bits is a quarter. And 2 bits is a quarter of the number of switches on an 8-bit panel. Because every panel has 8 bits to it. So the complete panel is called a byte. And the individual switches are called bits. So what you'll hear people talking about is they'll talk about a computer has so many bytes of information that it can hold. And they're talking about these panels. In 1980 was when the first computer was standardized, and it came up with a standard number of bytes or panels. You want to take a guess, this would go back to 1980, there's more in the computers today, but everybody would take a guess as to how many bytes or panels there were in a standard computer about 1980. 100? Okay, let's just have some numbers, we'll have them thrown out. Okay, we have 100 panels in 1980 as a possible guess. Okay, anybody else? Just throw out a number, anything.
256.
256 panels. Remember, we're talking 1980 here. Anybody else? Any other guesses? The actual answer is 640,000. 640,000, which we don't write it 640,000, that's too big to write. So we write 640K, or KB if you want to say kilobytes. Because it's like kilometers, you know, like a kilometer is 1,000 meters, or a kilogram is 1,000 grams. Well, a kilobyte is 1,000 bytes. So a 640 kilobyte computer means it had 640,000 panels in it. And now I'm going to show you what those panels look like. Okay, collectively, those panels have a name. I'll tell you what the name is in a minute. Here they are in this computer. This is the motherboard from the inside of this computer. A motherboard is a circuit board that lies flat at the bottom. If I was to tilt this computer up, you can see that there is a circuit board in the bottom there, lying flat. And on the circuit board that I'm holding in front of you are the switch panels that we're talking about. Here they are. Switch panels upon panels upon panels upon panels. Now inside every one of these black boxes are thousands of switch panels. So remember I told you they're called microswitches? The reason they're called microswitches is they're tiny. They're invisible to your eye. But they're designed inside these little chips. And these little individual black boxes are referred to as chips. And inside each chip are thousands of these panels. Now if you think that's impressive, back in 1980, I'll tell you today, you won't buy a computer with 640,000 panels. Unheard of to buy one today with so few. Today, the minimum computer that you'll buy when you go to buy a computer in the marketplace today will have 4 million panels. In fact, I'm going to stop using the word panels. Okay, I'm going to start calling them bytes, because that's really what they're called. And remember, every one of those bytes can store a number from 0 up to 255. Just remember, that's all they can do. That's all those panels can do. They have no other intelligence or any other mechanism in them. They can just store numbers from 0 to 255, every single one of them. But there's just so doggone many of them. There's 4 million of them. And that's almost unheard of today. Like, really, you're not going to go out and buy a computer today with 4 million. You know, most of you are going to go, if you look at the sheets that we've handed out to you, you're going to find out that you're going to buy a computer with more like 8 million bytes. And we write this as 8 MB, 8 megabytes. Mega means million, 8 megabytes, 8 million bytes. That's how we write it. The term for all this stuff is called the computer's memory. Another term for it is the computer's RAM. So collectively, all these panels are referred to as memory in the computer or RAM in the computer. RAM stands for Random Access Memory. And what it means is that all these circuits in the computer, all these little microchips, are randomly accessible in the computer. So it's called Random Access Memory. The point of the matter is there's a lot of it. There's a ton of it now compared to 1980, where you only had 640,000, and you thought that was a lot. And today you have, typically in a computer, 8 million bytes of memory, 8 million bytes of RAM. So if you're looking on your sheets, just some of you are glancing down right now, there's a section where it says random access memory, RAM installed, and it will show you how much memory you would get for your particular configuration of computer that you've chosen. So if you've chosen, for example, the home computing or school university computer, you're looking at a minimum of 4 megabytes or 4 million bytes of RAM, going all the way on up to 8 million bytes of RAM. That's today's standard that you'd be looking for. And that's what we're talking about, are those switch panels. Now let me tell you some characteristics about these switch panels. These switch panels hold information that you type in. So if you were working on the computer typing on the keyboard a letter to, say, Ralph Klein, every time you touched the keyboard and typed a new letter on the keyboard, that letter would get stored in one of the switch panels up here in the computer's RAM. Every time you touch the keyboard, you light up one switch panel, and that one switch panel stores one letter of the alphabet, and it stores it in one of these panels. Now you're probably thinking, well, wait a minute, you just told us a moment ago the computer doesn't understand numbers, much less letters of the alphabet. How is the computer going to know when I type the letter A? How's it going to know what to do? Computers don't know what the letter A is. They don't know what B or C is either. All they know is numbers. And every time you type a letter in the computer on the computer keyboard, it is stored as a number. For example, the letter A is stored as the number 65. Now, if it was up to me, I would have made it 1. But since I didn't design, the code, we'll let the engineers do what they want. And you know that B would be 66, all the way down to Z, which is 90, if you worked it out. Anyway, that's how the computer stores a letter. So if you type the A on the keyboard, the computer converts it to 65 and stores it on one switch panel in the computer, and that is 1 byte taken up to store the letter A. 1 whole byte taken up to store the letter A. You might be thinking, well, how's it going to know that it's an A and not the number 65? What if you type 65? Then does it think it's an A? How's it going to know 65 from an A? There must be more to the computer than just the RAM. The RAM is what's holding what you type, but something else has to make a decision as to whether it's a letter or a number, and something else has to also be able to perform the math. For example, remember we said if you want to store the number 65,025, you have to store 255 on one panel and 255 on the other panel and multiply the two panels? Well, something has to make that decision about performing that multiplication and performing that math. Does anybody know what that particular chip is called in a computer that does that? Processor, right. It's called a microprocessor or CPU. CPU stands for Central Processing Unit, or it's sometimes called the microprocessor. It means the same thing. And let me tell you what the microprocessor does again. The microprocessor has 2 main tasks. It makes decisions and performs calculations. Okay, what I mean by makes decisions, it means it has to be able to make a decision when you type in A that it knows it's an A, not a 65. So it makes those kinds of decisions. And it stores the information in the computer and remembers that that's an A and not a 65. It makes those decisions. And it performs calculations, which means, like I told you a minute ago, if you had to work out the number 65,025, it would make the decision to use 2 panels and multiply the 255 by the 255. The microprocessor makes that decision. Understand? It's a very, very, very important circuit in the computer, a very important chip in the computer. And here is the microprocessor on this motherboard. I told you this is the motherboard from this computer. Here it is here. This is from 1980, this computer. And this microprocessor is made by a small company called Intel. You may have heard about it. Intel? Just kidding, they're not a small company. If you've heard of Bill Gates, he's a small company too. They made this CPU or microprocessor. This is an old one from 1980, and it's called the 8088 CPU. And this is the microprocessor on this motherboard that makes the decisions and performs the calculations. And that's the other very critical component of a computer. Now, there's 2 main things to consider when you're looking at a microprocessor, and that is the manufacturer is one consideration, and the other one is the performance of the microprocessor. How fast is that microprocessor? For example, if you had to hire somebody to add numbers for you, and that's all they had to do all day was add and subtract and multiply numbers, would you want that person to be fast or would you want that person to be slow? Well, you want them to be fast. So what you want when you're looking for a microprocessor is a fast microprocessor. And by fast, we mean that it performs math calculations quickly and makes decisions quickly. So you want a microprocessor that's going to think fast and perform calculations quickly. Very, very important part of the computer. I have to tell you about one more component that's very important on the computer. And before I do, I'm going to ask you to think about this. Based on what I've told you so far, if the computer was equipped with all this memory, 8 megabytes or 4 megabytes, I don't care how much, and a CPU or microprocessor that can perform math and make decisions, if that was the bulk of the circuitry in it, you tell me what would happen when you did this, turn the power on to the computer. What would be your anticipated response based on what I've told you was the circuitry that I've put in? What would the computer know how to do by itself? Is there anything in here? Right now, we've just turned it on for the first time, so everything in the memory is empty. There's nothing in there. Okay, so we flip the switch on, there's nothing in here. So there's nothing in here that's going to be able to make the computer perform. Okay, so what else did I tell you about that can make the computer perform from the moment you power it on? Is it the microprocessor? No, the microprocessor just performs math and makes decisions, but it hasn't got any information to work off yet. So there must be one other circuit or one other chip in the computer that's responsible for the minute you hit the power button that some programs are going to work immediately upon power up. And there is. It's this chip over here in the top part of this motherboard. It's called the ROM, or Factory Read-Only Memory. Let me tell you about the ROM. It stands for Read-Only Memory. And what it consists of are factory pre-programmed instructions, or factory instructions on what to do upon power up. What to do upon power up. So in other words, you power up your computer, and there's a whole bunch of instructions in here that tell the computer what to do the minute that power comes to the motherboard. Now, the types of instructions that are included in here are instructions like check to see if a keyboard is hooked up. Check to see if the memory is there. Kind of important, right? Check to see if the memory is in the computer. Because if there's no memory in a computer, how's it going to function? Check to see if there's a CPU. Kind of an important thing to have in a computer, right? So it's a bunch of pre-programmed instructions that checks the computer every time you turn the power on. Has to. And then after it's finished checking everything, it turns control over to something else I'm going to talk about later. But for now, it's responsible for checking what's hooked up. And that chip is called the ROM. It's a very important chip because, as I said before, if you don't have that in there, there's nothing the computer can do upon power up. The other important thing about this chip is when you turn the power off to the computer, like I turn it right off here, all the instructions that were coded into this chip are saved. They are remembered. Because if the instructions in this chip were not saved, it would mean the next time I turn the power onto the computer, where would it get its instructions from, how to turn itself on and check itself? So these instructions that are in here are permanent instructions. So the feature about the ROM is that it contains permanently coded instructions that never go away even when the power is turned off. So it would be equivalent to you going into your basement, say turning on a bunch of lights in your house, going into your basement and turning the power off to the basement. Now, when you turn the power off to the basement, do the light switches all of a sudden go like this? No, the light switches all stay where they were, wherever they were. And when you turn the power on the breaker back on, everything comes up just the way it was before. And that's what this program is like. It just starts everything up the same way it was before. Now, this is a very important circuit because unlike the RAM does not remember what was in it when you turn the power off. So when you have a letter in there, let's say you've typed a letter to Ralph Klein, and you're working on it, and then you just say, gee, I think I'll go out now, and you turn the computer off. Well, when you come back and turn the computer back on, that letter to Ralph Klein is no longer there. It was just in this temporary area holding it while the power to the computer was active. So RAM is referred to as, the term they use is volatile. Volatile meaning that it doesn't hold anything once the power is gone. Whereas ROM is non-volatile, it holds all its coding and all its instructions even when the power is off. And the same thing applies for the CPU. The CPU is a factory-programmed microprocessor, and it has instructions inside what to do depending on the information it's seeing. And that does not lose any of its instructions when you power off the computer either. So the CPU, or microprocessor, is permanent, and the ROM is permanent, and the RAM is not. The RAM does not hold information when the power is turned off. I'll just summarize by telling you the three key components of the computer that you have to consider when you're buying a computer. And one of them is the RAM. And as far as the RAM goes, your primary concern is going to be, when you're looking to buy a computer, is how much is there? how much RAM is there in the computer. How much, not how much money, how much you get. Okay, not how much is what I mean. Okay, the next thing is the CPU or microprocessor, and your concern there will be how fast is it? Because with the CPU, you're concerned about how fast it is, how well it performs. So this is a speed consideration. This is really what you're concerned with. And then there's the ROM. And the ROM, you don't have an awful lot to say about. The ROM is pre-programmed. It just goes through some basic system checks when you turn your computer on. So the ROM is basically, you know, I'll say it this way, you get what you get. Now, in some cases, if you're having a computer custom built for you, in other words, if you go to a store that will configure a computer for you, you can actually specify the brand name of the ROM that's put in there. And there's 4 main brands. If you look at the very top thing on your sheet, the ROM, which is also referred to as the ROM BIOS, BIOS stands for Basic Input Output System. And there are 4 main people or manufacturers that make ROM BIOSes, and they are AMI, that's American Megatrends Incorporated. American Megatrends Incorporated. Nobody ever calls them that. They just call them AMI. There's Award, which is another company that makes a BIOS. Phoenix, and another small company you might have heard about, IBM. Okay, so those are the 4 main companies that make BIOSes for computers. And you can be sure if you buy an IBM brand name computer, you'll get an IBM brand name BIOS. If you buy a compact computer, it might have an Award BIOS in it. It might have an AMI BIOS in it, or it might have a Phoenix. Certain manufacturers vary from time to time depending what's available at the time that they're building the machines. So I wouldn't be too worried about it. I wouldn't be too terribly worried about it. They're all good BIOSes and they all basically do the same thing. You're far more concerned about the CPU and you're far more concerned about the RAM from your own perspective. Computers only work with switches inside operating on and off. There's a lot of them. I'm talking millions. And we're talking millions of panels. Remember I told you when we say 4 million bytes, that's 4 million panels. Each panel has 8 on it. So that's 4 times 8, 32 million bits. So that's 32 million switches inside the computer that could be going on and off doing different things. It gets mind-boggling. And that's why, you know, people are sometimes impressed. They say, gee, the computer can do so many different things. Well, it can't. It can only turn a switch on and off. But it has so many of them. That's why it can do so many different things, because it's the combinations of ons and offs that represent what the computer is doing at any given moment. It's amazing, but that's all that's going on inside. Switches going on and off. And ever since computers were invented to the present day, and I'm willing to predict on into the next century, they're still going to work on the same principle. Switches going on and off. I don't know that there's going to be any other innovation or remarkable event that will occur other than switches going on and off of some kind. The nature of the switches may change, but the concept of switches going on and off will be all that computers function on. Let's take it just one little teeny step further. We told you that computers operate with panels that have 8 switches on them. 1, 2, 3, 4, 5, 6, 7, 8. And this worked fine up to about 1982, 83. Every computer had 8 switches on each panel. And they were all individual panels. So the next panel would start here. 1, 2, 3, 4, 5, 6, 7, 8. And the next panel would start here. And there's lots of them. After using the computers for a while, people were wanting to do more things with them. And the biggest thing that happened in the early 1980s was people wanted more graphics on the computers. Up to 1980, 1982, 83, everything was text. You know, you wanted to do something, accounting, it was text. If you want to do word processing, it was text. There's no such thing as putting a picture into a word processing document. There's no such thing as having graphs in your accounting program. If you want to make a graph, you drew it by hand on paper. You could have the numbers, the computer could print the numbers out, but it couldn't do the graph. So what happened was as time went on, people wanted the computers to do more than just handle the numbers and the text. They wanted to handle pictures, graphics, all kinds of neat things. Later on, we're getting into sound and all kinds of new things that are happening with computers. So the engineers realized that they have a bit of a bottleneck here because they could only pass the information through the computer in a pathway that was 8 bits wide. This is called an 8-bit architecture. Everything is constrained to the so-called 8-bit architecture. Now, I'm going to give you an analogy. Imagine we had a 8-lane highway from Calgary to Edmonton, heaven forbid. But no, let's say we did. An 8-lane highway from Calgary to Edmonton. And let's imagine that I tell you that the speed of that highway is constant, 70 miles per hour. That's the speed. So we have an 8-lane highway and the speed is 70 miles per hour. Now, when I'm talking about speed, think of that as the microprocessor regulating the information going through the computer. Remember we told you the computer microprocessor, the important factor is speed of the microprocessor? Okay, so we're thinking of a computer that has 8-bit panels all through it and a microprocessor that can think at 70 miles an hour or drive 70 miles an hour while it's thinking. Okay, that's all we've got. That's your limitation. And that can handle text and that can handle numbers and that's about it. Then somebody was to come along and say to you, well, how about we do this? What if we open up a bigger highway and put 2 of these switch panels side by side? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And we're going to make ourselves a 16-bit panel. Now, it's still 2 bytes, but they're side by side. In other words, all they've done is they've said, instead of having the 2 bytes one after, let's put the 2 bytes side by side and think of it like one big highway. Now, suddenly I'm going to tell you that that's a 16-lane highway, and I'm going to tell you that the speed limit is still 70 miles an hour for now, just for now. Will you get to Edmonton any quicker? No, it's still going to take you the same time, provided you don't get picked up on radar. But can you move more volume to Edmonton in a given period of time? Yes. And it's moving volume of information through the computer in a given period of time that is critical to processing more information. So if you want to start handling graphics and you want to start handling pictures and stuff like that, you've got to be able to move more information through the computer in a given period of time. So what the engineers did is they re-engineered the computer so that every panel was side by side. And they not only did that, they also were able to re-engineer the CPU or the microprocessor to be twice as fast. So the highway sped up to 140 miles an hour. Now, does that look like they're going to move more stuff through the computer? Okay, so this new architecture that came along in the mid-1980s was called 16-bit architecture. And the obvious advantage of it was twofold. One, RAM was reconfigured to be still 2 bytes. It's still 16, it's 16, it's still 2 bytes. Just understand me, it's still 2 bytes. Some people say, well, oh, you mean you've got 16-bit RAM switches? No, you don't really have 16-bit RAM switches. You have 2 8-bytes side by side, and it looks like a 16-bit switch as far as the microprocessor is concerned. The microprocessor almost kind of sees it that way, but it really is still 2 individual bytes side by side. However, the speed was greatly increased. Let me tell you where it is today. 16-bit architecture is old by today's standard. It was mid-1980s. We're now talking mid-1990s. So the computers are not engineered with 16-bit architecture anymore. Any computer you're going to buy today has 32-bit architecture, meaning they have 4 bytes side by side for the pathway. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. Big highway. The speed, instead of being, it's not 70 miles an hour. It's not 700 miles per hour. More like 1,400 miles per hour. In other words, we're telling you that the speed relative to this time frame of when we had the earlier microprocessor at 70 miles per hour, we're talking about a 20-fold increase in the speed of the CPU, as well as increasing the width of the highway to 32 lanes. You can push a lot of information through a computer when you have 32 lanes operating at 1,400 miles per hour. That's a big, big improvement. And that is how computers are engineered today. Now, here's how it works. The RAM in the computer, the RAM is now engineered on the computer to be 32 bits wide. Remember, once again, don't let me confuse you. It's still 4 bytes side by side, but it's 32 bits across. Remember, I told you that every single switch panel can hold a number from 0 to 255. And every one of those numbers from 0 to 255 also could represent a letter of the alphabet. So if we go back to the earlier picture we had here, and if we type the word like car before, the C might be stored in this switch, the A would be here and the R would be here. So that's the word car. It would take 3 panels to store the word car, and they would have to be accessed one at a time. So the microprocessor reading this would say C, A, R. It would see it one at a time. It can only take the information that fast, and it would take it at 70 miles an hour. Now, with the new configuration, car would fit on one panel, C-A-R. It's not even filling it. We could have the word card on that one panel, and it would blast through the computer's information processing bank as one word, car, not C-A-R, and it would see it all at once, and it would be blasting through at 1,400 miles an hour. So there's a big difference in terms of the physical realm of what's passing through the computer in a given time period with a 32-bit architecture versus an 8-bit. And with a much higher microprocessor speed than we're talking about in the olden days. Now I better tell you how microprocessor speeds are really worded, so you don't go into the store and ask for a 1,400 miles per hour computer. Because I can just see somebody going, and yeah, my instructor said get at least a 1,400 mile per hour computer. None of this slow 70 mile per hour stuff. Here's how it works. The CPU speeds are measured in megahertz, which stands for millions of cycles per second. Millions of cycles per second. So computers don't think in miles per hour, they think in millions of cycles per second, or megahertz. And back in 1980, when we showed you that first computer in 1980 had a speed of 4.7 megahertz in 1980. And remember, that was only through an 8-bit architecture. Today's computer have speeds typically of, say, 100 megahertz. So that is what? Close to 20 times faster than the speed of a 1980 computer. So when you're looking at an ad for a computer, you will see a reference to the megahertz speed of the computer in the ad. And what they're talking about there is the speed of the microprocessor. Now I want to tell you the names of the microprocessors that are on the market today. The CPU is obviously a pretty important thing to be looking at when you're looking at buying a computer, because it controls the speed and the operation of the computer. And the most common CPUs on the market today are made by a company called Intel. Now there are other companies that make CPUs. Don't think that it's just Intel. Some people think, there's only one company that makes them. Well, Intel is the major manufacturer. And the two main microprocessors they're marketing right now are something called the 486 and the Pentium. Has anybody ever heard of those terms, the Pentium or the 486? Okay, so when you look at an ad and you see that it says it has a 486 in it, it means that it's got a microprocessor which is a 486. And that's just the name, the numerical name that Intel gave to that microprocessor. And it's a fairly fast microprocessor. It runs at a very high speed. If you want something even faster, you look at a Pentium microprocessor. Now you might say, well, what's the difference between a CPU that's a 486 and a Pentium? Well, remember I told you that everything was based on 32-bit architecture? What does 32-bit mean again? Well, the Pentium is 64-bit. It has 8 switch panels side by side by side by side. Now that is only in the microprocessor itself. The actual RAM on the computer will still be 32. You understand? In other words, the RAM is 32 across, but inside the chip itself, it processes the information coming in 64-bit chunks. So it could actually handle 2 32-bit completely full panels in one cycle, thinking it through. It doesn't have to process the first 32-bit cycle and then the next 32-bit piece of information. It can handle 2 all at once because it has a 64-bit wide internal architecture. If you were to have a 486 that was rated at a speed of, let's say, 100 megahertz, and a Pentium that was rated at a speed of 90 megahertz, what would you guess would be the faster chip? What? The Pentium is. Yeah, even though this looks faster as a number, this is still handling the 32-bit chunks one at a time. This is handling the 32-bit chunks twice as fast. So in a sense, relative to that, you could think of the Pentium as 180 megahertz relative to the 486. It isn't, but I mean, you can think of it like that. So you see how the numbers are starting to come together and how it's starting to crystallize in your mind a little bit about what all this stuff means? This is important because when you go into the store and they're talking and they're throwing these numbers at it, you want to be able to sort of have some mechanism of evaluating in your mind what that means in a tangible sense. If you think of it relative to the highway model that I gave you, of the 8 lanes versus the 16 lanes versus 32 lanes, and the fact that you now have 64 lanes inside the Pentium chip, and you think about not only the number of lanes that you have to carry traffic, but how fast the speed limit is through those lanes, you start to get an appreciation for how fast data is pushing through these computers. Awfully fast. So the CPU is a very important part of the computer.